So now today we'll discuss complex numbers. So first we need to know what is the theory of complex number. Where did they come from? Okay. So for that we must know the concept of quadratic equations. As we know, let's suppose we have this quadratic equation. X squared plus 2x plus 3 is equal to 0. Okay. Now let's find out the roots of this quadratic equation by the quadratic formula. So what does the quadratic formula say? That the roots of this quadratic equation are minus 2 plus minus under root 2 square minus 4 into 3 into 1 divided by 2 into 1. So this is minus b plus minus root d, which is the discriminant. Okay, and the value of discriminant is b square minus 4ac divided by twice of a. Now we can see that the value of discriminant is negative over here. So what we get is minus 2 plus minus under root 4 minus 12, which is under root minus 8 divided by 2. Now as we know that negative numbers are not allowed under the square root. Okay, so this is definitely not a real number. So we put these types of numbers into the category of complex numbers or imaginary numbers. Okay, so what is the significance of this complex number? Okay, what will we say? Let's say this is minus 2 plus minus. This can be written as under root 8 into under root minus 1 divided by 2. So this is nothing but minus 2 plus minus 2 root 2 divided by 2 iota. Now I have introduced a new term here, which is iota. Okay, this is a spelling of iota and it is represented by I, which is nothing but square root of minus 1. Okay, so it is pretty much clear that iota square will be equal to minus 1. So this is the base of all the complex numbers. This iota is the base for all the complex numbers. And we have a whole new chapter and a whole new topic on these types of numbers. So let's see all the operations on the complex numbers. So first we must know that all the roots which are not real. If I have a quadratic equation ax squared plus bx plus c is equal to 0, I can have two possibilities. Either the roots can be real or the roots can be imaginary, right? Now roots will always be of the form m plus iota n or x plus iota y. Now this will be the imaginary part and this will be the real part. For the case of real roots, I will have x plus iota y and the value of y will always be equal to 0. In the case of real roots, the value of y will always be equal to 0. In case of imaginary roots, the value of y is not equal to 0. Right? So these numbers, let's say example 2 plus 3 iota or 5 plus root 6 iota. In this case, the imaginary part is non-zero. In case of real numbers, this will be something like this, 2.5 or 2 or 5. Okay. So these are all the real roots and these are the imaginary roots. Apart from these, we have purely imaginary. Now what is the meaning of purely imaginary is that we have no real part. In this case, in case of imaginary roots, we have a real part and we have an imaginary part. In case of purely imaginary, we have only the imaginary part. Okay, so these will be something like 3 iota or root 6 iota. So in this case of purely imaginary, we have the value of x is equal to 0. Okay, so this is a concept of roots of a quadratic equation. Either we have real roots or we have imaginary roots. Under the imaginary roots, we have purely imaginary roots. Now what is the meaning of purely imaginary roots? We have no real part. Okay, so it is pretty much clear that if we have an imaginary root x plus iota y, we can say that this is a complex number where x is the real part and this is a imaginary part. Okay, so now we'll do all the operations on this complex numbers. that how we add two complex numbers or multiply or subtract or divide. Okay, and what are the other applications of this complex numbers. So let's start with operations on complex numbers. So the first operation is equality. When I say that one complex number is equal to the other complex number, let's say first complex number is x1 plus iota y1 and the other one is x2 plus iota y2. Now the real part of the first complex number is x1, real part of second complex number is x2. Similarly, imaginary part is y1 and y2. Now see, if these complex numbers are equal, okay, a complex number we usually denote by z. If z1 is equal to z2, okay, so this is a point to know that we usually denote this complex number by z or any other number like w, okay, this will come later on. And if these two complex numbers are equal, then we'll have the real parts, both the real parts must be equal and both the imaginary parts must be equal separately. So we'll have x1 is equal to x2 and y1 is equal to y2. There is no other way in which two complex numbers can be equal. Both their real parts and their imaginary parts have to be equal. Okay, if I want to say that z1 is greater than z2, is this possible? Actually, this is not possible. Okay, we can't compare two complex numbers because we have to compare the real parts separately and the imaginary parts separately. Okay, and in the whole, two complex numbers can never be compared. So we can never tell which complex number is greater or which complex number is smaller. Okay, we can only tell about the equality, that they will be equal if the imaginary part and the real part will both be equal. Okay, so this is the basic concept. The next is addition of two complex numbers. So if I want to add or subtract, addition or subtraction of two complex numbers. Now if I say we have to add z1 plus z2 or we have to subtract z1 and z2, so what will we do is x1 plus iota y1 plus minus x2 plus iota y2. So if we have to add two complex numbers, we have to add the real part separately and we have to add the imaginary part separately. Okay, there is no other way. We can't add a real part into an imaginary part or imaginary part to a real part. We have to add or subtract real part separately and imaginary part separately. So this will come out to be x1 plus minus x2 plus iota y1 plus minus y2. So this will be the result if we add two complex numbers. Okay, the real parts will be added separately and imaginary parts will be added separately. Okay, what if we multiply these two complex numbers? Okay, what will happen if we multiply two complex numbers? So in this case, these two complex numbers will get multiplied as we used to multiply in case of real numbers. Okay, as we used to open brackets in case of real numbers, like x1 plus iota y1 multiplied by x2 plus iota y2. Okay, so what will we get? We have to multiply first this x1 with both these numbers and y1 with both these numbers. So I will get x1 x2 plus iota x1 y2 plus iota y1 x2 plus iota square, because there are two iotas in this multiplication, iota square into y1 y2. Now we know that the value of iota is nothing but under root minus 1, as I told earlier. So therefore iota square, this will be equal to minus 1. Okay, so this will be minus 1. So this whole term will become minus of y1 y2, which is a real number. Okay, so this term can be written as minus y1 y2. Therefore the real part of this multiplication of complex number will become x1 x2 minus y1 y2 plus iota x1 y2 plus y1 x2. Okay, so multiplication will give us 4 terms, out of which 2 will be real and 2 will be imaginary. and they have to be added separately. Okay, real parts have to be added separately and imaginary parts separately. Okay, now I have to introduce a new term over here, which is conjugate. Okay, before we discuss the division of two complex numbers, I have to tell you what is a conjugate of a complex number. As we studied in case of quadratic equations, that the roots always happen in the conjugate pairs. Okay, if one of the root is 2 plus root 3, then the other root, okay, this I am talking about the real roots of a quadratic equation. If one of the real root is 2 plus root 3, the other root has to be 2 minus root 3. Okay, these two are called conjugate roots. Okay, similarly in case of complex numbers, okay, if one of the complex roots is 2 plus root 3 iota, the other root must be 2 minus root 3 iota. Okay, and these two are conjugate to each other. Okay, so if I see that, what is the definition of a conjugate of a complex number? If I have x plus iota y, so its conjugate will be equal to x minus iota y. So this was in the case of real roots. This is the meaning of conjugate roots in the case of real roots, and this is the meaning in case of imaginary slash complex roots. Okay, so this is a very important concept which we need to know. So as we discussed, that if the complex number z is given by x plus iota y, okay, then the conjugate of z will be given by x minus iota y. And how do we denote this conjugate of z? We just put a bar over the z. Okay, so this z bar will denote the conjugate. Okay, so let's move on to the next application, which is division of two complex numbers. Division of two complex numbers. So if I have two numbers z1 and z2 and I have to divide these two complex numbers, let's say this is x1 plus iota y1 and the other one is x2 plus iota y2. I have to divide these two complex numbers. We have to remember a small concept which we learned in our foundation classes, that if we had an irrational number in the denominator, what did we used to do? We used to rationalize the denominator. Okay, rationalizing the denominator means we have to get rid of this under root or this irrational part from the denominator. And how did we do that? By multiplying this by 3 minus root 5, so that we can have the identity of a plus b into a minus b, and this will become a square minus b square, 3 square minus root 5 whole square, and the irrational part will be shifted on the numerator. Okay, so this is the concept of rationalizing the denominator, which we learned in our 9th classes. So what we do when we divide two complex numbers is we start by get rid of this imaginary part from the denominator, and what we'll do is we'll multiply this by x minus iota y2 divided by x2 minus iota y2. Okay, this will not make a difference because these things are equal and they can easily cancel off. But what is the need of this is that this will convert it into x2 square minus iota y2 square, and the numerator will become as if we are multiplying these two complex numbers. So this will be x1 x2 plus y1 y2 plus iota x2 y1 minus x1 y2. Okay, so now if we observe the denominator, this thing is x2 square and this thing will become plus y2 square. How? Because this can be written as iota square y2 square. So the denominator will become x2 square plus y2 square. So if we divide two complex numbers, what we have to do is we have to get rid of this complex number from the denominator and we have to rationalize the denominator. Okay, we have to make it a rational number. Okay, how will we do that? This will become x2 square plus y2 square and the numerator will remain the same. Okay, so this is the basic application of division of two complex numbers. Okay, so next let's take a simple question on these applications. Let's say I have these two complex numbers, 2p plus q plus iota times p plus 2q, and the other complex number is p plus q plus iota q square minus 3. Okay, so these are two complex numbers. Let's make it minus and make it plus so that the question becomes more simpler. So I'm saying that these two complex numbers are equal. Okay, so what is the condition for that is that the real parts and the imaginary parts have to be separately equal. Okay, so we can say that the real parts, which are nothing but 2p minus q and p plus q, they have to be equal. Okay, so what condition we get from here is p is equal to twice of q. Okay, and the imaginary parts will equal as well. Okay, in case of imaginary parts, we have p plus 2q is equal to q square plus 3. Okay, so now I have to find the values of p and q in this case. So what will the two complex numbers be? Will they be any different? No, the complex number will be the same because the real parts and the imaginary parts are equal. Okay, so what do we get from here is 4q is equal to q square plus 3, and we get q square minus 4q plus 3 is equal to 0, and this can be easily solved for the values of q is equal to 1 and 3, and subsequently we can get the value of p. Okay, so we'll get the complex numbers. So the lesson from here is, if the two complex numbers are equal, we have to equate the